Okay, so as I promised, we're going to talk about quantum numbers. I'm going to introduce to you some quantum numbers that we use to describe the electrons and their energies within atoms. Okay, and also other properties, not just energy, but also what we call the momentum, the magnetism, right, and also the shape of our orbitals that our electrons reside in. Remember, in our Bohr's model of our atom, we kind of always thought that electrons were going around in circles, or maybe spheres around a central atom. But we're going to learn that there's actually a little more to our model that we're introducing now. All right, so the principal quantum number, our n value, that is like, when comparing it to the Bohr model, that's like saying the different shells. N equals 1 here for the first one, n equals 2, n equals 3, 4, 5, 6, and so forth, right? And n represents the energy of the electron, its n value, because the higher the n value, the farther away it is from the nucleus, and therefore more potential energy that it has. All right. To transition from 1 to 2 requires energy. To transition from 3, 4, 5, 6, 7, 8, or 9 to 10, for example, it requires less energy than it does to go from 1 to 2. So every orbital that you go out, you get shorter and shorter in terms of distance. Okay? So these are our n value. And this is also the shell that your electron resides in. Okay? L is what we call our secondary quantum number, and it divides the shells into subshells. So M is our magnetic quantum number. It divides subshells into individual orbits. Okay? So N values roughly relate to the distance the element is, or the electron is, from the nucleus, and also is a number like 1, 2, 3, 4, 5, 6. It's never 0, right? We just say the shell that an electron resides in. You can have elevated or excited states. So if you just have one electron and one proton, right, that one electron would or could always be right there, right? You think of it in the lowest, n equals 1. However, if it's excited by electricity or by heat, right, it can jump up to excited orbitals, right? So just because you don't have electrons in higher orbitals, it doesn't mean that there aren't higher orbitals for a single electron to get excited into. So n will equal some value between 1 and, usually you're not going to see higher than 7 or 8 or something like that. But that's our n value. L, on the other hand, can only equal a value from 0, again, up higher to, 5, 6, or whatever. But it'll always be less than our n value for a given electron. So, for example, if n can equal 1 through, let's say, whatever, they generally say infinity, but, you don't get values much higher than 7 or 8 usually. Then L, the lowest value that L will be is 0, but the highest is going to be n minus 1. All right? And the number of possible L values is equal to the n value. So if n equals 1, for example, if n equals 1, what can L equal? What can L equal? Yeah, if n equals 1, what can L equal? L can equal... I forget. Well, remember, L can only be as high as n equals 1. Sorry, L can only be as high as n equals... L can only be as high as n minus 1. All right, n minus 1. So, if n equals 1, the highest L can be is 0, And what did we say the lowest L could be was? 0. That's right. So if n equals 1, L equals 0. If there's a scenario where n equals 2, then that means there's 2 possible L values. And again, the highest would be n minus 1, so 1. Or you could have L equaling 0 for a scenario where n equals 2. Okay? We talk about these quantum numbers and what their possible values are before we really explain them. But this is the way it's always been done, and it will generally help you. You'll be able to understand once you have a grasp of what L values are, what quantum numbers are possible. The next quantum number is m sub L. All right, m sub L equals the possible m sub L values are negative L all the way up to positive L and all the integers in between. So, for example, if I have L equals 0, what can m sub L be? Negative 0 or positive 0? That's right, and that's still just 0. If I have n equals 2, L equals 1, what are my possible m sub L values? Negative 1 up to positive 1? That's right. So what is negative 1 up to positive 1? Negative 1, 0, and positive 1. Very good. Excellent. For this scenario over here, what is my possible m sub L value? Well, it's just 0, right? Because if m sub L can only be positive or negative L. That's right, 0. Excellent. So those are our 3 quantum numbers, there's 4 altogether. There's one called m sub s, and m sub s is always either positive or negative 1/2. Positive or negative 1/2. And this m sub s here value indicates the spin. So these are our quantum numbers. N can be 1 through infinity. L can be 0 to n minus 1. M sub L can be all the way from negative L up to positive L and any integers in between. And m sub s is always going to be either a positive 1/2 or a negative 1/2. N represents the energy or the distance from the nucleus. L is the shape of the electron cloud, right? The orbital. M sub L is the position or the angular momentum, the angular positioning of the orbital itself, and m sub s is the spin. Atoms have a property called spin, where they kind of respond to a magnetic field the way magnets do, and kind of the way a magnetic top would. So we call it spin. Okay, good. Now, our L values, which are 0, 1, 2, 3, 4, 5, right? They have letters associated with them. So the letters that they have associated with them are S, P, D, and F. So let me write this down for us. The L values, like, again, if L equals 0, 1, 2, or 3, possible L values, then we have letters that go along with this. And the reason we do this is because we often talk about the N value and the L value together. And if they're both numbers, then it can be confusing. And so we have L values to kind of, we have letters that go along with these L values. And the letters are S, P, D, and F. S, P, D, and F. And what that does for us, again, is it becomes a little bit easier. I can refer to the N value and the L value simply by saying 1S or 2P or 3S or 3P, right? 3 being the N value, P being the L value, okay? And so if I say P, the L value that I'm thinking of is 1. If I say S, the L value that corresponds to is 0. And these letters, S, P, D, and F, are from initial descriptions of the atomic spectra, the different colors that these different elements would release. Sharp, principal, diffuse, fundamental. But we don't have to remember those words at all. And in fact, because L values represent the shape of the orbital, oftentimes people think the letter S stands for spherical. And that's fine. You can think of that as being spherical because orbitals that have an L value of 0 are spherical. All right. Very good. So I'll tell you right now while we're on the topic, there's my sphere that I'll draw, right? L values are spherical. L values of 0 mean that the orbital is spherical. L values of 1, p orbitals, have this kind of a shape. And they can either be oriented along an x, y, or z axis, z axis in a Cartesian coordinate. Oh, let me move this up out of the way. Okay. So our s orbitals are spherical, and our p orbitals are kind of what we call a dumbbell shape. All right. Very good. D orbitals, we'll talk about their shape later.